Hello everyone, welcome to this first week of the second module. In this module we're going to talk about rigid body dynamics in Houdini, and we will cover a whole bunch of topics and workflows related to them, like how to make multiple objects collide together, how to fracture them, the constraints, creations of bodies, and much more. A rigid body object is nothing but a piece of geometry that you maybe need to reshape in an optimal way, which has some kind of dynamics properties. And once we send this to a top network, we can create a simulation using the proper Houdini solver engine and without any animation. We will start this week by creating a simple setup with the main nodes that makes the rigid body simulation possible. And hopefully you will understand the workflow along with some tips that we'll provide to you. Then we're going to go one step further and with a more complex exercise that I'm going to show to you. And this is a very quick preview of what we should achieve by the end of the week. And this is intended for you to apply the previous knowledge of the rigid body dynamics. Of course, there's a lot of things missing here, like, I don't know, the smoke, the drifts, fracturing, but we're going to add all of this in the following weeks, along with the ground crack effect to the asphalt. In this exercise, you will face a lot of real production problems, and that is the main point of doing it, because it will make no sense to work always with cubes and spheres. Here you will apply the basic RPD workflow to complex geometry, and we will show you how to face and overcome main issues. So let's get to it. So now that we are already in Houdini, let's, as always, save the scene to be more organized. And also, this will provide us with the $heap global variable, which is very useful. Let's go to File, Save As. I'm going to save the scene in this Module 2 Week 1 folder with the name of Week 1 RBD Intro 001 heap. To doing so, we can call this folder by just typing $heap whatever we want. Working with relative paths are always more convenient because we can have access to all of these folders by just adding a slash after $heap. For example, if we have a file node and we want to call the cars folder, we can just type $heap / cars / whatever. So let's save this here, and I'm going to create a geo node to start with. Let's call it RBD start, dive inside, and here I'm going to make a tower of boxes. To do so, let's first drop a box. Okay, so I'm going to push it a little bit upwards, and now this box is staying on center, on the ground. Let's make some copies with the copy and transfer node. Let's start with the x-axis by giving it a translation of 1.5, maybe more copies, 8, will be fine. Let's do the same with the z-axis. I can either Control-C, Control-V this node, but I think it's much more convenient to just click Alt and drag the node how many times as we want, as many times as we want. It's much faster and easy. So I'm gonna do this to make the Z copies. Let's give the same distance and with the same number of copies. And now we can create some copies on the y-axis. So let's just, again, Alt and drag this node, connect it to the first one, and give the same distance pointing to the y-axis. Maybe I'm going to need more copies, for instance, 25. Okay, now that we have a beautiful tower of cubes, let's just, to have a nicer simulation, I would like to rotate this a little bit on the y-axis. And by doing that, we will also need to change the pivot. So let's add here a 5 and in the Z2. Yeah, that will work. Now, in order to have our simulation with this, we have to convert this geometry to packed primitive. This is because Bullet solver also uses only points representing each piece of connected geometry with a transformation matrix. If the geometry were more complex, we should also have to reshape it, but we'll see this later. For now, let's drop an assemble node here, assemble, and we can turn on the packed geometry. Now, you still see the same on the viewport, but if I double click here, you can see we have 1 point for each connected set of primitives. And this is required for the bullet solver to make a simulation. And furthermore, it will save a lot of memory. You can compare this amount of points with this. Here we have 12,000 points and 9,000 primitives. What this is doing is just let me split this interface, and I want to see the geometry spreadsheet. Okay. What this assemble node is doing is creating first the name attribute on the primitives. Let's go to the primitives. And here, if I go to one single box, imagine this is the primitive 0, the box 0. This is gonna add a string value of piece 0 to each primitive that are connected to this geometry. So the attribute name will have the same value to each primitive connected. Then if we pack this geometry, this will promote to the points, and each piece of connected geometry will have the same name attribute. And although this will work fine, you should get used to split this in 2 steps, because when we have to create constraints between pieces, the proper workflow is to first create the name attribute, in the output of which the constraint will be created, and later on we'll proceed with the packing. So let's just turn off the create pack geometry, and I'm gonna duplicate the assemble node, and this will be the first step, and this the second step. Here we don't need to again create the name attribute, so let's only turn on the pack geometry. So now I'm gonna drop a null node here. Gonna call it, for example, ode pack geo. And before starting with the simulation, let's go over the other nodes and rename it properly. This could be named as pack geo, create name attribute, z copies, y copies, x copies, and this is the main geometry. All right. So now that we have the tower boxes properly packed and with a name attribute per piece, let's start with the RVD simulation. First, I'm going to create a dot network. Let's connect the output of the null to the first input, names to sim, and let's jump inside. There's a thing that every simulation needs, and this is a solver which processes our data. Houdini has 2 rigid dynamic solvers. The first one, and this is the one Houdini has been using for a long time, is the RVD solver. It can be useful nowadays when we have complex geometry, but when we need to simulate thousands of pieces, this solver gets really slow and deprecated. So to work with multiple objects, we'll always use the bullet solver. This is much faster and more efficient. But the one I recommend you guys to work with, though, is the rigid body solver. And this is because, as you can see, this is a digital asset. If we dive inside, you can either find the bullet solver and the RVD solver. But the things that makes this solver interesting is that it already has a multi-solver system created. And this will allow us to apply any external pop node we want. So to import our packed geometry to the top network, let's add a RVD packed object. And let's connect it to the gray first input of the rigid body solver. Then we only need an external force to make them move and an external object to make it collide. So I'm going to put a gravity node here, and let's merge it to a ground plane. Remember that the collision object should always be in the left. Let's set the output flag here, or maybe in the output. Okay. So in order to call the cubes, I have to go to the geometry source and set it to the first contact geometry. I can rename these to cubes. And before pressing play, let me show you the geometry representation of the RPD packed objects by going to the bullet data and turning on show guide geometry. I have to turn off the display geometry for now, and we'll talk about the other parameters in a bit. If I turn the display geometry off, you can see in a blue color the actual colliding geometry. This is not going to be always the same as the one we input to the dot network. It will strongly depend on the shape of the pieces we have. For now, let's just turn off the show guide geometry, turn on again the display geometry, and I'm going to hit play to see how fast bullet is. Great. So now let's talk about some interesting parameters we can find on the RPD packed object node. Once we select the RPD packed object, we can see a bunch of different parameters that could potentially change the speed and behavior of our simulations. I would rather go with another simple object, so I've prepared some scenes in order to see the main different results by tweaking these parameters. Let's jump to object level, and we'll start by the collision padding parameter. Let's frame the peak this time, and in this example, we'll show you how we can get totally different simulations by changing the geometry representation. Inside, we can see this time the input geo has to be reshaped. The default method is convex hull, and this fills concave regions of the input geo. The concave method is no longer supported by side effects and could lead us to problems and issues. And besides, is the slowest. The other ones are made by simple geometry. Therefore, the simulations will be very fast, but it will be not very realistic if we have detailed geometry. The collision padding parameter will have bullet to do the collisions and avoid the intersection between pieces. By default value, which is 002, is fine, but you can play with it and see what you get. Let's go now to the bounce example. I'm going to work with a sphere this time. Let's jump inside. And you can see how changing the value of the RPD packed object, the bounce value of the RPD packed object, which is located here in the physical tab, it will lead us to very different behaviors. Let's try by default value, which is 0.5. Let's try 0. And let's try 1. This value is going to multiply the bounce value of the collision object. In this case, is the ground plane. And if the product of all values, if the product of all the collision objects are greater than 1, the object is going to gain energy every time, and hence it won't ever stop bouncing. Let's try, for instance, to set this to 1.2, and the bounce value of the ground plane to 1.2 as well, and see what happens. Okay, so the friction is the resistance when the object has some contact with the collision, and we're gonna work with a cube this time. High numbers will make the object settle quickly, whereas low numbers or 0 will make the object slide. Let's try a friction of. Let's see what happens by default by default value. Let's put this value to 0. As you can see, this will never stop. And now I'm gonna make this into 10, for example. Cool. So let's see now the rotational stiffness parameter. Also this time I'm gonna use this peak. I have a little bit of rotation to it. And I have this simple setup when I'm gonna have this peak falling down. The rotational stiffness value, here we have, it will help to control the amount of rotation of an object. High values or 0 will add a great stiffness, and low values will allow the object to have more aggressive rotation. Let's again try the by default value of 1. Let's see what happens if I set this to 0. It doesn't even move. And same if this value is a high one, like 10. It barely moves. And finally, let's see how the density changes the simulation. This time I have 2 identical boxes. The first one is placed on -5. The second one is placed on 5 on the x-axis. Both of them are packed objects. So let's dive inside the network. So I'm gonna give them different densities and see how they react. I think this is barely visible, so I'm gonna hide the ground plane. Better. Okay, first let's see in the physical tab. This has a density of 1000. This has the same value as well. So let's hit play and see what happens. Okay, let's select both of them, and I'm gonna multiply this by 10. This will change every node that I have selected, this and this. Now they will have a density of 10,000. Let's see what happened now. Same result. Then let's tweak one of them, and you should see a completely different result. For example, let's grab the second one and lower this 10 times. Perfect. This is also helpful when we need more control on braking constraints. And it will be nice if you can go back to our box tower simulation and see how changing all of these parameters affects the outcome. Now that we have built a tower, it will be nice to destroy it. And that's exactly what we're going to do now. Let's start by creating some geometry to destroy the tower. And this time I will start with a simple sphere, but you can use any object you want. So let's drop in a sphere. I'm going to transform this to a better position. For example, I can go to the viewport, press enter, and move it this way, maybe a little bigger. Okay, that'll be fine. Let's push it upwards. Cool. Now let's drop in an assemble node, and since we are not gonna add constraints to this, let's just turn on the create pack geometry. And I can add a null node here and name it as out collision. Let's plug this to the second input. And before diving inside the DOM network, I would like to go to the, I think it's Z copies node, and I'm gonna get rid of the rotation. Perfect. We'll end up firing this object towards the tower, and to do so we need to set an initial velocity. So let's make this by creating an RBD object, and then we'll see how we can change the initial parameters. RBD packed object. Let's name this sphere. Merge it to the first one. And if I go to the first, I have to call the second context input here. And if I go to the initial state, we can see that we can change the position, rotation, velocity, and angular velocity around the centroid of each RBD packed object. Let's aim this sphere to the tower by giving it some velocity in the x direction. For example, let's try with 30 and see what happens. Gonna press play. Cool. Maybe I'm gonna make this sphere bigger and faster. Great. Now let's change the sphere to a peak geo. Should be in the same position. Let's rotate the peak 90 degrees. Okay, and now let's give it some angular velocity. For example, I can try the x value of the angular velocity with 360, for example. Let's see what happened now. Great. Working with the initial state app is only useful for test purposes. A cleaner way to do this will be to set the velocity on a sub-level and let the RBD packed object inherit the attributes by turning this option on. So I'm gonna set these values by default, and let's jump outside. And before sending this to the DOM network, let's drop a point velocity here. This is the new H17 node. And let's give it the same value. I think it was 30. You can see here in the geometry spreadsheet that the x component of the velocity is 30 now. So if we go inside and we press play, nothing will happen. The peak is falling down because of the gravity. But in order to the peak to inherit the velocity that we have set on the sub level, we have to turn on the inherit velocity from point velocity. Now if I press play, you can see the peak is receiving the velocity of the sub level. And this is useful not only here, but especially when we need to have more control on each RBD pack object that we send into the DOM network. So perfect, now you're ready to start with the exercise. Okay, so let's start this project by saving the scene to the proper folder. Let's go to Save As, go to the week 1 folder, and I'm gonna save it as week 1 RBD cars 001. And now we have to import everything related to this shot. And if we were in a company, we'd probably find this depending on which department it belongs. For example, if we were to import the camera, we would find the files at the tracking department folder. The geometry will be in the modeling folder, animation in the animation one, and so on. For now, let's just import a camera. Which you're gonna find it in the Levic folder, this one. I'm gonna select it, select camera, and in the view tab, I'm gonna place the Valley sequence animation here. Sequence, this one. Okay, now we have the sequence on the background, and if I jump one level up, along with the camera, we have received the grid plane of this shot. But if we go to the object level and let's switch to the top view, we can see there's a weird rotation on the grid we have to fix. And I would like to scale this a little bit as well. So let's apply these transformations with a null node connected to as a parent of the Alembic. So we can always see on the object level what that we have to modify it. Let's name this as global transform. And I'm gonna rotate this on the y-axis. I have 3.1. Also, I'm gonna scale it by 10. Good. So let's now create a geo node. I'm gonna call it grid. Dive inside, and let's import the geometry of the Alembic with an object merge. I can press Shift W here, go to the P-plane, and drag this into the object one here. Let's set this into this object. Switch to the camera. Cool. So first, let's convert this to points and polygons with a convert node, as usual. And you can see that we at the end of the frame we need to scale this grid a little bit. So let's fetch a transform here. And before scaling this up, let's put the pivot on the center. Cool, now I'm gonna scale this a little bit in order to fit all the range. 1.5 should be fine. So now, since we don't need to render the whole range, we can trim this a little bit and set the start frame by 145. This will give us 4 seconds. And if you can see, there is an issue here, and this is caused by the far clipping of the camera. So let's go to the camera by select the camera. And let's go here on the far clipping value, and I'm gonna Control Shift click here to delete the expression, and I'm gonna multiply this by 10. So if I go back to our grid, now it's fixed. And before importing the cars, let's delete everything but the polygons on the main road. I'm gonna switch this to the wireframe node. I want to hide the other objects, so I won't see the, no, because I need, yeah, let's just turn off the Alembic import here. Okay, now let's switch to the camera. Cool. So to select these polygons, let's press A and select one of them, and with a middle click, select another one, and this will make a loop to the polygons. So let's again Shift A, select one of them, and middle click the one next to it, and they will be fine for now. So let's delete this, non-selected, and I'm gonna add a null node here and call it out grid. Cool. I'm gonna use this this grid to render the shadows and also to scatter the cars on it. Maybe let's go inside again to the transfer node, and let's scale this a little bit. The z-axis, I think, is, yeah. I'm gonna move it. Maybe rotate it a little bit. Yeah, that should be fine. So now let's import the cards. I will start by placing one of them, and then we're gonna procedurally import all the other ones. So let's create a geonode, name it cars, that inside, and let's fetch a file node. We have to go to the cars folder and select one of them. Okay, as you can see, the scale is really big. So the first thing we're going to do is to scale it down, the transfer node. Maybe this value, a little bit. Okay, I'm going to rotate it. And as you can see, this is sliding a little bit. So if I go to if I Control 2 on the viewport and go to the front view by space 3, center the car. I'm gonna switch off the grid here. Then we can see the plane is placed above the car, so we have to raise the car a little bit. The value we need is 7. Cool. So far so good. And we'll end up this part of the exercise by scattering some cars on the road. In order to do so, I'm gonna first import the ground object. So let's select this null node, out grid, drag it here, and I can hide the other objects now. We have the grid here, and I don't want the cars to be scattered all along the road, so let's trim it a little bit. I'm gonna go to the last frame and select the region of the road that I want to instance the cars on. This will be fine. Delete, non-selected. And now I'm gonna place a scatter node here. Maybe we'll start with 10. Cool. And turning off the relax iteration option will make the scatter node faster, but then they are more likely to intersect with each other. So let's keep this option activated. To place the card on these points, I'm gonna need the copy to points node. And on the second input, let's connect the points. and the geometry in the first one. And here we go. We can try if everything is working good so far. And to do that, I'm gonna show all the objects here. And let's move through the timeline. Right now, you can clearly see that the scale of the cars is a little bit strange. And this is because when we imported the grid and we copied the cars on the points that we scattered, we no longer need the cars to be raised. So what I'm gonna do now is just zero up this value. Now if I move through the timeline, you can see that the things are going fine. Before starting with the simulation, I would like to import our 9 different cars and randomly scatter them into the road. Then I'm going to show you how to add some variations of the transformation and the shader of each one. However, firstly, you need to understand the two methods we could use, and when I'm going to choose the for each workflow rather than the old copy stand one. So let's jump into this example I've prepared for you, and let's try to understand how this works. On one hand, we have the copy stand method, and on the other hand, the for each method. In both cases, we want to instance a peak head geometry to 1000 points and give them some random rotations to each one. The copy stand method needs the copy stamp node. And if you go to the stamp tab, you need to turn on this stamp inputs before copying. And then we can start creating the variables. I'm gonna create a new variable. I'm gonna call it rot for rotation, and let's set this value to an expression. In this case, I want to create some random values between -60 and 60 for each point. So let's type feature 1 random of ptnum, and it will go from -60 to 60. Let's also pack the geometry before copying it. Otherwise, it can overload your memory. This is what I've done in this example, but instead of single values, I wrote an expression here because I want to see how fast is one method and compare it to the other one. I changed this to -frame and I multiply it by 4. So here is the result. So lastly, let's go to the transfer mode, and I have to go to the Y rotation value, and I have to type the following expression: stamp, and this is the path of the stamp node, which is called copy1. We want to have access to the rotation variable, and then this is the default value in case it doesn't find any other one. So since now we have a time-dependent animation, I would like to see how many frames per second this animation is running. And in order to do so, let's go to the viewport options, typing V. I go to the guides tab, and I'm going to turn on the show time option. Cool. Let's jump into the first frame, and let's hit play. Now you can see these peaks are randomly having a rotation on the y-axis, and the velocity is pretty slow. You can see we are running at 1.3 frames per second. So now that you have seen this, let's jump into the for each method. This time I'm going to use a simple copy to points node. So let's copy this peak 1000 times on the scatter node. What I need here and before calling the for each method, I need to pack an instance this peak, because we don't want the whole geometry to be copied, but only the packed geometry of it. So right now I have 1000 packed primitives. Then I'm gonna call for each primitive loop, place it here, and let's see how we can add some random rotations to each one of these peaks. This loop will run wherever we have between the begin and the end nodes for each primitive we input. Here, every primitive means a packed geometry object, so we are modifying each one of the peaks instances on the points and merging them together in the end. In order to give them a random value to use on the rotation, I need to have access at the iteration value. In this case, this will go from 0 to 999. So if I can grab this number and give it a random function, I could apply the result on a transfer node. Right now I need something that gives me this iteration number, so we have to create a metadata node. So let's grab the for each begin, click on the create meta import node, and if I select this new node and I go to the detail attributes, and to do so I need to split this again and go over the geometry spreadsheet, selecting this node, going to the detail tab, and here, not now because I don't have any geometry selected, but if I go to the for each that comes after the peak instance, I can find the iteration I'm running this very moment and the number of iterations. And those are details I can call from any node inside the for each loop. So instead of showing what's happening inside this transfer node, I think I'm going to delete this one and create a new one. And let's start from scratch. So if I display this transfer node, let's enter. This is the peak I'm working on. If I go here at the end of this for each, you can see that nothing happens to the copied geometry because I'm not doing any transformation to them. But to test each one of them, I can toggle the single pass option, and with this slider we can go to each iteration we want. Cool. So let's select again the transfer node. I'm going to frame this peak, and before rotating this peak, I need to be sure that the transformation is made on the centroid of this geometry. So before adding any value here in the Y rotation axis, let's centroid this expression. Okay. Now we can call the detail attribute of this metadata node. I changed as you can see, I changed the name to a shorter one. So the name of the attribute is called iteration. Then I'm gonna go to the transform to this parameter, and I'm gonna type detail because it's a detail attribute. Let's give it the path, which is /it. Close the quote. It's called iteration, and this also needs a by default value, which can be 0. Let's close this function, press enter, and I can evaluate this, and you can see now we have a value which is the same as the iteration we are right now. And if we merge all these iterations together and display the for loop, now you can see each one of the peaks is rotating by the iteration. But what we want is the same expressions as we had in the copy stand node. So what I'm going to do is type in the same expression, which is feed01 random of this value between minus path frame 4 times this and 60. I think this is the same. Enter. I have a typo here. Okay. Cool. Now it should behave the same way as the copy stamp method. So let's hit play and let's compare the velocity of this method. Oh, it looks something is wrong. Let me pause the video. And yeah, I have a typo here. I need to add one more parenthesis on this expression. Okay, right now if I select the end of the loop and I press play, you can see how fast this goes right now. It's like 5 times faster than the copy stamp method. Cool, though. So this is just a basic introduction to for each node. We'll see much more of them later in the following weeks, because for me it's a very important topic to know since it's used a lot in production. So now that we have some basics of for each loops, let's see how we can use it either to import the cars in a procedural way and to add some random variations of any parameter we want. Alright, so let's jump into the cars node, and here, as you can see, I've properly renamed all the nodes. And first thing I'm going to do is to use a for each to import every car we have in the cars folder. So this time, I don't want to loop over any point or primitive or packed geometry. Instead, I want to repeat the same operation of loading a geometry, and in each iteration I want to have an increasing different value every time. If I go to the cars folder, you can see they are named in a tidy way, which is pretty usual in production. And as you can imagine, we have to figure out a way to go over all these numbers here from 1 to 9. So this time, let's drop a for each number loop, and actually I'm gonna connect this to the transfer node. And if I go here and I see what's happening, this is merging, this is loading 10 times because I have 10 iterations the car. So as you can see here, I have 100,000 of points, and here we reach the million of points. To prevent memory issues, it's better to pack this thing before doing the for each loop. What we need now is to go over this number here, and we have to change this exact number to the corresponding iteration, which goes from 1 to 9. So let's call the detail iteration attribute here, the one you can find in the detail attribute, this one. Let's call it by typing here, by replacing this 1 by quote detail for each count iteration, which is the name of the attribute, and a 0. Let's close this, close the quote, enter, and it's complaining. Why is complaining? Because if you evaluate this, the iterations will always go from 0 to the max number of the iterations, from 0 to 10. But we don't have this 00 low poly dot object. The cars are going from 01 to 09. So what I'm going to do here is add 1 before closing the quotes. So this is going to take a while. So, once we have all these cars loaded, the following operations will be super fast. And we still have an error message here, and I think this is because we don't have the iteration number 10. So I'm gonna put this on manual mode because I don't want this change to be cooked. and I'm going to change the iterations to 9. So now this is going to go from 1 to 9. Let's set this to auto update again. You can see the cars are loading. And here you go. So if I middle click this, I can see all of the 9 cars are loaded. Now let's see how we can scatter some cars on the road randomly. First, I think it's a good idea now that we have all the cars loaded to save them in a file. This will save us a lot of time every time we open our scene. So let's drop a file cache here. I'm gonna call it packed cards. And I will save this in a folder called cars, packed card, cars, PGO-SC. You have to set this to a current frame. So let's save this and load it. Cool. Now we have all the cars packed and save it here in this folder. So now we can, after loading the cars, we'll do the following. I want, for each point on the road, to choose a random car of the 9 we have and copy the kind to the car to the point position. To do this, I need from every point to generate a random attribute going from 1 to 9. And then we'll grab this attribute and we're going to delete all the cars except this value. For example, if this point gives us a 6, we want to delete all the cars but 6. And we want to place this car to this point position. And we'll do this to every point we created on the scatter node. So first I need to generate this random value, or at least to generate a different value for each point. Let's create a for each point loop. Let's plug the points into this loop. And I'm gonna make a metadata node, and I'm gonna call it it from iteration, because I don't feel like typing all of this every time I need to get into the iteration attribute. Cool. Now I can jump to the cars file, and before deleting them, it's a good idea to give them an index, just to make sure that we get what we want once this is done. We'll see this in a bit. For now, let's drop an enumerate node connected to the cars, and this will give us an index attribute and a value from each point, from each packed primitive we have. Okay, so we're almost done. Let's create a blast node here and connect it. And I'm going to type an expression here which will randomly delete all the cars but 1. So first I need to go over the iteration value, this one here, and I'm going to do so by typing detail it iteration 0. This needs to be within quotes. Cool. Now we have this number, which is the number of the iteration. Let's turn this non-select node on, and I want to generate a random value from here. So let's type run. This has to be all of the functions and expressions needs to be inside the quotes. So I'm gonna put this here, run of this value. Let's see what we get. Okay, and now let's fit this from 1 to 9. So inside the quotes again, fit 0, 1, open, I'm gonna go here, from 1 to 9. Cool. This should work, but just in case, let's round it to an integer value by using the rint function. So rint, close this again, enter. Perfect. Here we have our random integer value from 1 to 9. Now we only have to add the copy points inside the for each loop and connect the blast and the for each begin together. So let's connect the template here and the primitives to copy here in the first input. Let's plug this to the for each end. Let's see if this is working. And here we go. We can prove that all the cars are being instanced by going to the spreadsheet. And if I sort this by index number, you'll see we have every car on the ground randomly copied. Actually, this is not true because the names of the cars went from 1 to 9. But once we have saved them, what we have is 9 cars. And what we are deleting here is not the name of the cars, but the point number, which is the packed primitive. So instead of going from 0 to 9, we should go from 1 to 9, sorry, we should go from 0 to 8. Because we have from 0 to 8 point numbers. Now, if I go again here, we can check this, and this is working as is supposed. And there is another way to check this. You can create a blast node here, and since we have this index attribute, I'm going to use it in order to make sure all the cars are being copied. So let's type here index. Let's start with 0, the lead node selected. Here we have our first car, and if I middle click this and drag to the right, I can go from 0 to the last instance of these cars. So it looks like all is working perfectly. And just in case you are tempted to do all of this with the copy stamp method, I'm gonna show you how it will work, and you will see that using for each loops are much worth it. So here on the side, I have this other workflow where I have this file importing the cards, and I would like to tweak the scatter sheet. For instance, let's first copy the template to this input. What I have here, let me set this to manual just in a moment. And what I have here is the cars are importing in this file node, and here I have the stamp expression. And this stamp expression is going over the copy stamp node and taking this variable, which goes from 1 to 9. So this is randomly taking cars from the cars folder and giving them random values from 1 to 9. Let's set the display flag here and set this to auto update again. This is going to take a long time because I have 100 points, so let me just break this, and I will set 10 points only. Let's wait until this is loaded. Cool. Now that we have our cars loaded, let's see what happened in this method if I change, for example, the seed. So I'm gonna go here, I'm gonna tweak this, I'm gonna change this number to, I don't know, 10. As you can see, using the copy stance needs to be cooked again, whereas with the for each loop, the method, it goes instantly. So if I go here again, and I change the seed, look how fast this is going. Also, we can make 100 instances, and you can see the cars are loading automatically. Super. Let's go ahead now and add some shaders to these cars. Before, let's play a little bit more with the for each loop settings by giving to every car a random Y rotation. I don't want to waste your time, so I have paused the recording, and in the meanwhile, I have organized all of this properly. So let's drop down a transform node here. And this is cool because you can either place it after the blast node or after the copy nodes node. I will drop it here, and we need to write almost the same expression we have in the blast node, which is fit01 random of the detail iteration node iteration attribute 0. Let's close this, and let's fit this value between -50 and 50 degrees. Cool. Remember, you have to put the centroid of each pack primitive to its center. To do so, let's type this expression that you already know. Perfect. We can play with the seed by adding more numbers here. We can play with the min and max values here, or we can just promote all of this. So now let's create a simple render setup to just one car, and we will apply it to the rest. Let's first blast everything but one car. This one, for example. And first, we need to create a new camera for rendering purposes, lights, and a new grid. So let's start with the camera. Let's select the camera. And I don't want the background in this camera, so let's go to the View tab, background image. Let's delete this. Cool. Let's create a new grid. Let's make them bigger. Where is it? Here. I want it bigger, something like this. And now let's bring the HDR we have in the texture folder. You can find it in the heap folder, textures, and HDR. Cool. Finally, let's bring also a distant light. And I want to split this for a second. Grab the distant light, and I want to rotate it to a better position. Yeah, something like this. Great. If we want to render any geometry, it has to be unpacked. So let's go to our car, and let's drop down a unpack node. No, not this one, but the unpack. Okay. Let's also add a material node. Connect it to here. And I can do this with just one step within this material node by adding as much tabs as we need for each group. Or we can also create a material node for each group we want to add a different shader. I would choose the second option this time because I think it keeps stuff more organized and it's easy to debug. So let's name properly all of these nodes. We'll start with the car paint. Also, we need a shader to the glass. We'll call it glass. Plastic for the tires and the interior. And then silver for the wheels. Cool. We don't want to spend much time on making textures and shaders, so let's just grab the ones we have here for free in the material palette. I'm gonna grab a glass shader. I'm gonna grab a plastic shader and silver shader. Here we go. And we don't have a car paint shading here in this palette, but we can create our own with the principal shader. So let's jump to a sub-level, and note that the order in which they are added, it does matter. That is, all these material nodes are here are going to override the first one. But this is fine because we want to apply the car paint as base color, and then all the others want to specific groups. If we middle click here on the AppPack node, we can see that fortunately all the elements have been properly named by groups. This will allow us to assign each material to each group in an easy way. We also can go to the material and we can open the group tab, and you can select any group where we want to have this material applied. Or we can just go to the viewport, press S, press 9, and now we can have an interactive way of select the group of polygons, just in case we wonder what's the name of what we are selecting. For example, this one has the name of low poly HDM44 car paint. Here the same with glass windows, plastic black, rims, etc. Another good tip is we don't need to type the entire name of the group. For example, if we would like to apply the car painting material to this low poly HDM4 car paint, we can just find a keyword that could work for all the cars and type it between the stars. That could be star, car, star. So let's start applying all these materials to all the groups of all the cars we have. As I said, I want this first material to be the base material. So I will grab in the material network this shader, which we could rename it as car paint. Let's go back by pressing Alt left arrow key. And then this is going to be applied to all the car. Let's go ahead with the glass material, select the material from the material network, and now we have to apply it to the windshields and everything that it has some glass in this car. To do so, I can go with the method, and if I select the windows, I can notice that there is a glass window named here in this group of polygons. So I can type everything containing glass, everything containing window. Enter. And now you can see this material is only applied on the glass surfaces. Let's do the same with the plastic material. Select it. And I want this to be on the tires. These ones are called plastic. So I'm going to type plastic. Also, I want this material to be applied inside the car to these polygons here. They are called interior. So let's type interior. Cool. That should be fine. And let's finish with the silver material. Maybe metal. and then we'll grab the silver material. And this is going to be applied on the wheels. Rims. Okay, so rims. Cool. Now that we have all shaders applied, let's go to the render view. Select the new camera, press render. And maybe we can tweak the light to have a better render here. So I'm gonna go to the scene view, select the distant light, it looks like I have some clipping issues, so I'm gonna go to the cam and let's change these values from a lower one to a bigger one. Let's select the camera. Okay. So I'm gonna grab this light. Let's move it a little bit. Let's see how it changes. Maybe more. I want to have a shadow. So I think there is a problem with the grid. Maybe it's misplaced. So let's go back to the object level. I want to change to the front view. Select the car. And if I press W for the wireframe, yeah, here we can see the grid. So let's move this grid up by 7 units. Go back to the camera and render this. Great. Now we are casting some shadows. Something like this. Yeah, that will work. So let's go to the material network and let's quickly set all these parameters. Going to the surface tab. I'm gonna lower the resolution a little bit for the sake of the speed. Click render. And I'm gonna start by pushing this value up, 2.5. 0.05. Maybe a little bit of metallic value. And a little bit of reflecting. You can also play with the code and code roughness values. Remember, it's a good practice to use the snap option to compare all the renders. So for instance, if I snap this render and I change a value, for example the metallic, I can switch between the render I'm doing right now and the last render. And I can snap as many frames as I want. Once we are happy with our basic car paint, let's jump up again and we'll see how to add some variations. If we don't care about the outcome and we just need some random colors to add to the cars, we can just create an attribute, a randomize node, and make some color random attributes. Let's go to the scene. And I made a mistake because I want this new random attribute, which is going to be called car color. I don't want to generate random values for each point of the unpacked geometry, but I want it to generate random color values, random vector values, sorry, for each car. So what I will do is to drop this before unpacking it. Let's rename this as rand car color. And as you can see, it has 3 dimensions. So this is fine for now. Let's bypass the blast node to have all the cars. And I'm going to display the material for each car. Cool. Then if I dive inside the material network, we can call this attribute by bind and set the name of the attribute, which is car color, and set the type, which is a vector or 3 floats. Cool. So now I want to connect this vector value to the base color. Let's do it. And we need to turn off the use point color just to avoid overridings. Let's set the new camera. And let's render this. Don't mind about this warning, doesn't matter. So something is not going wrong, something's going wrong. Let's see what's happening. Group, car pane. Oh yeah. Before, as you can see, we have no car color attribute here, neither on the primitives or anywhere. So before binding it to the material network, we have to transfer this car color attribute from the packed geometry to the unpacked one. So let's do it by car color here, and let's see what happened now. This should work. Yeah, now it's working. Cool, right? Okay, let's stop this and let's do the same, but this time I would like to create variations on the roughness. So I'm going to drop down another attribute randomize node, call it randomize rand rough. The attribute name is going to be called rough. And this time I need a float. So I'm going to lower down the dimensions to 1. Cool. Again, we need to transfer this new attribute called rough. Let's go here, unpacked. Then transfer this rough attribute. Let's go to the material network. And now I can do the same as we did with the car color vector attribute, but this time I'm going to bind the rough float new attribute. So it's going to be called rough. And the values of this attribute are going to work fine because they're going to go from 0 to 1. So let's plug this into the rough parameter. you can check that this is going to be overridden by this attribute. Let's go back again, display the material, and now if you go to the render view, press render again, great. So you can see that right now every car has a different roughness. And of course, we can apply the same method to create any random value we want and apply it to any parameter of any shader we want. I would like you guys to play with it a little bit before continuing. Now, imagine the director told us to randomly choose between some specific colors. In this case, we've got to use a for each loop to apply only one of the total shaders we have in the material network. So let's replicate this problem by making a copy of the principal shader. This one, we want to make maybe 5 of them. Let's call it color 0. We're going to have 1, 2, 3, and 4. And let's change the color of each one. First red, second blue, then yellow, purple, and black. So this time I want to have variations on the number after the color name. Let's jump again into the sub level, and as you guessed, we're gonna need a for each loop. So let's create a for each primitive loop again. Let's connect it here before the unpack node, and let's copy this node inside. As usual, we have to unpack the geometry first. Cool. Now I need the iteration number to generate random values for each one of the cars. So let's create a meta import node. We can rename it as color iteration, and in the material node, this one here, I want to have the iteration placed in parameters because it will look easier. So let's go to the parameter interface, and I'm gonna need an integer. Let's place it here, call it color iteration. Apply, and here I can type the expression you already know, which is fit01 random of detail. Let's search for the color iteration node. I want the iteration 0, and since we have 5 different shaders, this should run from 0 to 4. Cool. So let's change this name to color 0, and I want to change this 0 for this expression. So let's copy parameter and paste the relative reference here. Looks like we have an error here. Let me quickly debug this. This is working. Material, color, and okay. Let me pause the video for a bit. It might be a typo error. So here we go again, and Yeah, I had to add some another parenthesis here. So now it looks like this is working. Let's test it by hitting render. Looks like it's not working. Let's see what happens. I'm gonna go to the scene view. Okay, so select one, unpack it, car paint, group. Oh yeah, I typed this during the pause to see the difference and to find the error. So let's delete this because I want this material to be applied to all the geometry. Let's go to the end of this for each. Let's see if this is working. It looks like this is working because we can already see the difference in the viewport. Let's see how it's gonna outcome in the render. Cool. So definitely this is working. You can also change the seed by adding some number here. Perfect. So now let's grab all these other material nodes and paste it after this one. Hit render again. And now I can start watching the plastic material, the glass material are being applied to these cars. But still, we can see there are some materials missing on some of the wheels of some of these cars. So let's back to the scene view. And if you take a look at this metal material node, this is complaining because it's not finding any rims group. This could be because at some cars the wheels group, the wheels name can be rim, and to the other cars it could be another name. So let's just maybe press S9 and let's see how this is named in this car, for example. Here it's called rim. Oh, rim, no rims. So let's delete the S. Okay, it looks like it's working. Perfect. So let's pack all of this again, and we can start with our simulation. But remember that you can't render pack geometry, so we'll need to unpack it after the simulation to make a render. I'm going to show you that trying to render pack in geometry is not going to give us a good result. Yeah. So here we're gonna do the render stuff, and then we're gonna unpack the cars again. So if I unpack this again, it should be rendering properly. Now we will end the rendering setup by creating shadows on the ground and setting the matter nodes ready to start. Before that, let's set the display flag here. This will make the things much faster. So let's jump to the object level. And if I turn on the first grid, you'll see this needs to be bigger. But remember that we are importing this grid into the cars object to scatter some points there. So if I change the size of the grid, everything is going to change. Instead, let's drop a transfer node here. And I'm going to add a null node and call it out grid render. So we are going to render this. Let's jump into the transfer node, and as always, we need to center the pivot. Cool. Now we can start increasing the size of the z-axis. This should be fine. So now the material we need to apply to this grid is called Shadow Mate, and you can find it here in the material palette. So let's just drop and drag this to the grid. And I'm going to go to the render view and see how it looks. Choose the correct camera, hit render. So we've got a mate material applied on this grid now, and if I look closer and I change this to the alpha, I can see this is casting a very dim shadow. So let's change the distant light a little bit to have a larger one. I'm going to go to the scene view. I will select the distant light. Let's face a car, frame a car, sorry, and maybe this rotation will be fine. Let's see how it looks now. Cool. Now this doesn't look like correct, but it's exactly what we need, because we're going to multiply the shadow layer to its alpha, and we're going to place it on the background in comp. If you want to see the final result, we can change the background by opening this tab, going to the display options, and in the background tab, let's choose the sequence. Click apply, and here we go. We should split this in two layers, one for the cars and another one for the shadows. So let's go to the out network and rename this matter node to cars. Let's duplicate this, and this one is going to be called shadows. I want the first matter node to render only the cars. So let's go to the object tab, delete this, and let's force the cars to be rendered. Let's check the alpha. Cool. Now let's force the grid in the other one. First I have to change this to shadow matter node. Go to objects, delete this, and this time I need the force objects to be the grid one with the shadow material applied, and I need to force phantom to the cars. So let's select the cars. Let's see if this is working. Click render. Excellent. So finally, let's set a proper output to each one. Let's go to the cards, images, and here I'm going to change this to heap file render, and I'm going to call it cars.$f4 and exr. Remember to turn off the override camera resolution before sending this to render. And also you would like to render the whole frame range. Let's do the same with the shadows, images, and change this to, for example, car shadows, shadows $f4 and exr. Turn off this. Cool. Then we can end this by merging these nodes together with a merge alt node. Or we can also plug one to another. And this will change which is going to be rendered first. Remember also to change the camera to the one we need. You can find it here inside the Alembic track camera render, this one. And now we are ready to render. So if you want to use this, way of connecting the mantra nodes, you have to select the last node of the tree and click render to disk. If you want to use the merging method, you have to merge all the mantra nodes you want to render and press render here. Well, now it's about time to have some fun with rigid bodies. So far, what we have is our cars shaded with some variation, and they are properly packed. So let's go to the cars geometry. Let's display the packed geometry. I'm going to stop the render. Let's select the camera. And I can copy, I would like to save this again. And I can copy the file cache we already have here and paste it after the for each node. And I can name it as packed shaded cards. And let's save it into packed shaded cards, cars.pgo.sc. Cool, but actually, I think we should move the cars forward to have them in front of the camera, because they're barely visible on the first frames. So let's go to the import grid, and instead of trimming the road to these polygons, let's do it again. I'm gonna go to the first frame, select this one until here with this one, and with the A pressed, click here, shift this one, A pressed, and click here again, and I can delete this part of the road, unselect it. Cool. Let's go to this for each again. And it should work. So starting from here, let's first save this new cars placement. Perfect. So now I'm going to show you the RBD workflow you don't have to follow, and then we will compare it to a more optimal one. But first, and for the sake of the speed, let's add a wrangle node after the packed shade cars. And I want to delete some random cars by using the expression if random of ptnum which is each one of the cars is greater than some value, called run, for example, then remove point. Control Enter. Then now I have to create this channel here. And if I play with this slider, I can see this is the percentage of cars I want to remove. This is a script I use all the time to randomly remove some points and speed up the scene. Cool, so let's place a null node. After the wrangle, maybe rename this as random remove cars. I'm gonna call this in cars sim. So now let's jump back to the object level and let's create our dot network here and keep everything tidy. Let's call it sim. Dive inside, and now let's fetch all the nodes we already know to create a RBD simulation. And those are RBD packed object, rigid body solver, gravity, and let's add a ground plane. And merge all of this together. I can press L to organize all of this. And let's call the cars. And this time, I'm going to call the cars using a new feature in Houdini 17, which is if I go to this node, I can Control-C copy this node, go back to the sim, and Control-C in this parameter. Cool. Now be careful because the ground plane could be misplaced. Let's take a look at it, and yes, it is misplaced. So let's set the front view. And I'm gonna fix this by raising with 7 units to the y-axis. Cool. So let's set again the camera, and let's press play and see what happens. This is going quite slow, isn't it? So instead, let's see what happens if we turn this into boxes representation. Let's jump into the RBD packed object. I can call this as cars. And if I go to bullet data, I want to change this from convex hull. Let me show you how is the convex hull representation of these cars. And let's change it to box. Let's keep this representation. Let's press play and see what happens now. So as you can see, this is going way more faster. It's very important before starting a simulation that you optimize as much as possible the geometry, and in order to avoid long time simulations. So in this case, although it's more accurate to work with convex hull for each car, the final result will be very close as we work with boxes, and the speed will become way faster. There is an issue though we should fix. If I play this, you can see at the first frames we have a little bit of movement. So we can go to the rigid body solver and change the sleeping time from 2 to, for example, 0.05. And this will make the cars settle super quick until they get hit again. Let's now set our collision body to make these cars fly a little bit. To do so, I will create a simple sphere and make it collide with the cars. Let's do it here at the object level by creating a sphere. Call it call from collision, type inside. Let's set this to ghost other objects. And remember, you always have to set the display off of the DOM network. Let's go here. And now we have to create our animation with a transfer node. Let's make the sphere bigger. I'm going to split the viewport. Let's see what we got. All right. Let's make this into a polygon. And the animation should be super fast. And the sphere shouldn't be super big neither, because the scale will affect the impact. So I'm going to place this, let's set this to the camera. I'm going to place the sphere here. Let's see. Okay. I'm going to give it several frames until here, for instance. This is going to be the last frame, and it's going to travel until it gets here. And let's set the starting position. Maybe this is going to go too fast. Let's set the key here. Or we can also set this to auto key changes. Now every time we make a change, it's going to make a key for us. Let's see how it goes. I think it's going too fast. So let's jump to the last frame, press enter, move it a little bit backwards. And if I press V, that will open the animation editor. So I can select all the animation curve and make it to straight. Let's see what happens now. Yeah, let's try this. So let's make this sphere into a deforming collision object by selecting the collision geometry. And inside the shelf, in the collision tab, you have to press this deforming object. Now, if we dive inside the call, we can see we have the geometry and the VDB representation. Let's go back to the simulation.network. And let's see if this works. I'm going to press L again to organize this. And yeah, let's try this. Yeah, it's kind of cool. Let's see what happens if we add the rest of the cars by bypassing this node. Press play again. Cool. I'm gonna leave it like this, but we expect from you guys to improve the simulation. Finally, let's import these cars by using a DOP import node. We can do it, for example, here inside the cars. Let's do it here, DOP import. And here I have to choose the DOP network I want to import the geometry from, which is the sim. And I wanna type star RVD star. No, sorry, I think I rename it as cars. So let's type cars. And the import style should be fetch geometry from DOM network. Let's see if this is working. And here we go. We have successfully imported our pack geometry. As we said, before rendering this, we have to unpack this geo. So let's connect this unpack here, set the display to the outcars null, and maybe we can create a new mantra node to test renders. So let's create a new mantra PBR. Gotta go to the render view, select the new one, mantra, and let's hit render. Make sure that we are gonna render the nodes that we want. Okay. No, not this collision object. Cool. Now to add some motion blur, we have to turn the motion blur option on. So let's go here and on the rendering tab, turn on the allow motion blur. And we can also compute the velocity of each point by adding a trail node as it is after the unpack node. So let's pause this render. Let's go to the card geo. And let's drop down a trail node. Set this to compute velocity. Connect it here. And furthermore, we must set the geometry velocity blur to velocity blur. By default is no velocity blur, but you should change it to velocity blur. This is going to take the velocity attribute from the geometry. So let's hit render again. Check if the motion blur is properly working. We can just render a small version of this. Cool. If we needed more motion blur, we can go to the trail and scale up this velocity scale, for example, 5. Let's see what we get. Obviously, this is too much, but let's set this again to 1. And before rendering all the scene, we need to cache all the simulation. So let's go here, and let's add a file cache node. Plug it here. I'm gonna name it this as sim cards. And we can save this simulation into $heap sim cards, the version which is 001, and cards underscore sim dot $f4 dot bgo dot sc. Make sure that this time we want to save the whole frame range, and let's hit save to disk. And I'm gonna pause this until it's complete. And it's done. So I made a playlist for you with the cache geometry. And again, we expect from you to improve the simulation. Okay, so that's pretty much it for this week. Enough. If I miss something, I will add an extra video for you. I hope you guys enjoy it, and you have a lot of work to do, a lot of parameters to tweak, and I encourage you to have something different to this example, because it's much better if you use your creativity with the knowledge you've gained this week and create something similar to face new problems. Again, thank you for your attention, and see you in the next week.